And you can never quarantine the past, but you remember in December that I won't need you when I'm gone, and if I go there, I won't stay there.
Let's continue our discussion of the structure of the set of all R-module homomorphisms between M and N. We'll prove the last two parts of proposition 2 in section 10.2. And the first part focuses on composing R-module homomorphisms. So let's say M, N, and L are all R modules. So if you have phi, an R-module homomorphism from L to M, and psi, an R-module homomorphism from M to N, then psi following phi is an R-module homomorphism from L to M. So it's helpful to just look at the picture. If phi is an R-module homomorphism from L to M, and then psi goes from M to N, then you can first do phi and then do psi, and you go from L to M and then M to N. So the composition goes from L to N. So you can't compose just any two R-module homomorphisms between different R modules. You need it to be that where the first one lands is where the second one picks up. So the codomain and the domains need to be compatible in this way. All right, well, one thing you could do is if you have R-module homomorphisms from M to itself, then you can compose that with another R-module homomorphism from M to itself. Just take M equals N equals L here, all of them being the same. And in that case, with addition defined as we defined in the previous video, where we took phi and psi being two R-module homomorphisms, and we defined phi plus psi by saying what it does to any element X in M. So you can define addition as before, and you can define multiplication as the composition of functions. That turns the set of all R-module homomorphisms from M to itself into not just an abelian group, but into a ring. And that ring always has an identity. Okay, so if you believe that this is true, then this ring gets a name. This is called the endomorphism ring of M. Sometimes instead of writing hom R M M, we'll write instead end R M. So end R M is the set of all R-module homomorphisms from M to itself. Or sometimes it'll be very clear what ring we're talking about for these R-module homomorphisms, and we'll just write end M. I'll try to remember to write end RM whenever this comes up. Okay, so why is this called the endomorphism ring? Well, the elements in this endomorphism ring are called endomorphisms. So endomorphisms are R-module homomorphisms where the two modules that you're mapping between the two R modules are the same. So it's an R-module homomorphism from an R module to itself. So I'll say something now about the proof of 3, and then I'll say something in a few minutes about the proof of 4 after pausing and erasing. So the idea here is we have these two R-module homomorphisms, and we can compose these functions. We want to show that what we get is an R-module homomorphism. And at the very beginning of this lecture, we proved the first part of this proposition, which gave a nice way to check when a function between two R modules is an R module homomorphism. So we want to use that characterization, part 1 of proposition 2. So let's say R is an element of the ring and X and Y are elements of L. Psi following phi is an R module homomorphism if and only if you apply it to R dot X plus phi and you get the thing from that proposition. So let's look at what happens when we apply this to R dot X plus phi. Well, okay, what is psi following phi? It means you first do phi to R dot X plus Y, and then you do psi to the output. And that's just the definition of the composition of functions. But we know that phi is an R module homomorphism. So by this characterization, we know that phi of R dot X plus Y must be r dot phi of x plus phi of y. This is by this characterization 1 applied to the R module homomorphism phi. So what happens when we apply psi to this element of the R module M? Well, this is r dot phi of x plus phi of y. And because psi is an R module homomorphism from M to N, we know what happens when we take psi of r dot something plus something else. So if we apply 1 to psi, we see that this has to be equal to r dot psi of phi of x, whatever that is, plus psi of phi of y, whatever that is. Okay, but now we're just going to use the definition psi of phi of something is psi following phi of that something. It is the composition here. So what we're getting is r dot psi following phi of x plus psi following phi of y. That's just using the definition of the composition. And look at that. We take psi following phi and apply it to r dot x plus y, and we get r dot psi following phi of x plus psi following phi of y. And this is exactly the characterization that we need in order to show that psi following phi is an R module homomorphism. So we can exactly use the criterion 1 and see that psi following phi is an R module homomorphism. Okay, so this is a nice argument because it uses this characterization 3 times. I'll point out you don't have to do it this way. You could also check that psi following phi is a group homomorphism and that psi following phi applied to r dot x is r dot psi following phi of x. So you can think through the details of that as well. Now I'll pause and erase, and I'll say something about this last part of this long proposition. I'll just say a little bit about the proof of this last part of the proposition. So first, if you have an R module homomorphism from M to M, the domain and the codomain are the same. So you can certainly compose R module homomorphisms from M to M. You can first do one, then do another. So this composition makes sense with this setup here. And by the fact that the composition of 2 R module homomorphisms from M to M is also an R module homomorphism from M to M, then this composition of functions takes in 2 elements of hom R M M and gives you another one. So this function composition multiplication gives a binary operation on this set of R module homomorphisms from M to M. All right, so now we know this set of R module homomorphisms is an abelian group. And we have this binary operation, this multiplication. We have to show that this multiplication turns this abelian group into a ring. So we have to check the axioms for what it means to be a ring. And I'll leave the details to you. All of these pieces are straightforward, but you really do have to check all of the things that need to be true for a ring. So for example, you need this multiplication. Think of this as r times x plus y has to be r times x plus r times y. That in a ring, multiplication has to distribute in this way. So we need that phi following psi plus chi is phi following psi plus phi following chi. And you can check that this is true by checking what the 2 sides do to each element x in your R module M. So this is just one. You need to satisfy another distributive law as well. Multiplication is associative because function composition is automatically associative. There really are some details to check here, and I encourage you to write down a fully detailed proof of this result once. It'll be helpful for you in working with R module homomorphisms. So I won't say anything more about that. What I'll say is there's one other part to this proposition, which is this ring has an identity. So what is the identity? Well, it's the identity map from M to itself. You have to check that this really is an R module homomorphism. You can use that characterization 1, that I applied to r dot x plus y is r dot I applied to x plus I applied to y. And it is clear that that is true. And now you have to check that it's the identity of this ring, that if you take the product or the composition of functions, I following phi, or in the other direction, phi following I, that you really just get back the R module homomorphism phi, which is pretty clear. So there are some details to check here, but there is nothing surprising or challenging in the proof of this result. So I'm going to pause and erase, and then I'll just talk very briefly about one question of, well, where do these endomorphisms of a ring M come from? In general, that's a complicated question to answer, but I'll tell you one place that you can find a bunch of endomorphisms of your R module M. Let's briefly talk about one last issue. Where do endomorphisms come from? And in general, that's a hard question to answer, but here's one idea. So in the case that R is a commutative ring, we can consider this map from R to the set of endomorphisms, the ring of endomorphisms of our R module M, defined by taking the ring element R to the endomorphism R times I. So remember, there was this whole discussion about hom R M M. In the case that R is a commutative ring, is not just an abelian group, but is also an R module with this action of the ring. So the identity map from M to M gives an endomorphism, and R dot I gives an endomorphism as well. Okay, great. Well, you could ask, what does this look like? And in fact, it's more than just a map. Where does X, or where does R plus S go? It goes to R plus S times I, but that just is R times I plus S times I. Where does a product go to? This is actually a ring homomorphism from R to the endomorphism ring here. And so you might think, well, yeah, that's great. Now I get some copy of R inside the endomorphism ring. But you have to be careful because this map doesn't have to be injective. So I'll take a really extreme example. If R is Z, so we're just looking at a Z module M, so an abelian group M. Let's take the simplest non-trivial one we can think of, Z mod 2Z. So what does this correspondence look like? Well, you just take an element of Z to the endomorphism given by that element times the identity. So 2 goes to the endomorphism 2 times the identity. But what does 2 times the identity do to any element? Well, it just sends X to 2 times X, which is just X plus X, which is 0 for all elements X and Z mod 2Z. So the endomorphism we get over here is the 0 endomorphism. So it's just not true that this map is injective here. But when R is a field, our R module M isn't just any old R module. It's a vector space over this field. And in that case, this map, where you take your field element R to the endomorphism R times the identity, is injective. And let's see why that's true. Well, we just have to say that these different elements, R times I, these different endomorphisms, are all different for different elements of your field R. So why are they different? Well, they send non-zero elements of your vector space to different places. So let's say X is not 0. What does R dot the identity do to X? Well, just by definition, I mean, it sends it to R dot I of X, which is just the scalar multiplication in this vector space, R dot X, whatever that is, some vector. If you take a ring element S, where does S dot I send X? It sends it to the scalar multiplication S dot X. And in a vector space, if X is a non-zero element and R dot X equals S dot X, well, what has to be true? These two things are equal. You subtract from the axioms of a vector space, that is R minus S dot X. So we have this vector must be equal to 0. But if X is a non-zero vector, that's true if and only if R is equal to S. Okay, why is that true? Since we haven't talked much about vector spaces, let's really think about it. Suppose you have a non-zero element X in your vector space, and alpha dot X is 0 for some non-zero alpha. Well, what happens when we take the scalar multiple of both sides here by alpha inverse? So we're in a field, alpha is not 0, alpha has an inverse. We get alpha inverse dot alpha x. Well, that is 1 dot x. And to be a vector space, you need to be a unital module. I mean, part of being a vector space is that 1 dot x equals x for all elements of your vector space. But now we have x, and this must be equal to 0 because clearly alpha inverse dot 0 is 0. And this is a contradiction. Okay, so what have we seen? In the case that R is a field, we have our R module M, which is our vector space over our field. This map taking elements of our ring to these particular endomorphisms of our R module M is injective. So what do we get? We get a copy of R inside of the endomorphism ring of our R module M. And okay, so Dummett and Foote say this quickly. This is a subring. Really, I mean, we have one element in the endomorphism ring for each element in our ring R. So like R is inside of this endomorphism ring as a subset. But in fact, this map is more than just a map. It's a ring homomorphism. So we actually get an injective map from the ring R to this endomorphism ring. So the image of R is a subring of the endomorphism ring. This subring is called the subring of scalar transformations.